Good morning, everybody. Sorry for the rant last week at my low emotional level after Lucinda Williams was telling me everything was wrong and coming to the realization that it was. In the past week or so, you folks sent me a lot of comments on the channel, words of encouragement, suggestions. Speaking of which, Tomek, I'm going to do a video about this little guy here. I think you'll recognize your concept in it. Nonetheless, to me, it's always great to get feedback from you folks, and I love the suggestions. Everything you comment on, I take to heart, and boy, if I can utilize it, I absolutely will. And for those of you, Juan and of course Tomek, that have offered programming help, I will definitely take advantage of it when the need arises. But thank you all so much. As I mentioned at the closing of last week's episode, number 35, I had mentioned I'm working on a different idea. And I've taken that through a lot of testing since filming last week's story. I think I'm onto something with that. I'm not ready to go into all the details in this episode with it, so I'm going to give you an overview and show you some test results, and next week we'll go into more detail, assuming I can do something with those test results and make corrections. Now, for our first part of this, I just want to do a quick overview of what we're going to talk about today to sort of set the stage for where we're going. I'm calling this episode number 36, Finding a New Direction. Using train tracks to solve the problems. You heard that right, train tracks. But I'll get into more details of that a little bit later. Our current objective to move forward with this project is to improve precision of the feedback system to achieve better localization. That's really what it boils down to. I need to achieve the ability for the Zoomy control software to know where the Zoomy is at any given point to a reasonable expectation of precision. I suggested last week that I wanted to be within 1 millimeter, and that's a very lofty goal with what we're working with here. And I'm willing to back off on that a certain degree. I've got a little wiggle room on that, but not much. Now, Jeff Libovich, a fellow that I know, he commented, back off on that, and he's right. He and I are in the same industry together, so we kind of understand how critical it is to achieve the level of precision we're after, but also the understanding, is it really necessary? And so that becomes an important piece of feedback that helps me to rethink what I'm really doing here. But nonetheless, I've got to focus on getting it as best as I can at this stage to make everything better further down the road. Interesting way of putting that. So what we're going to be looking to achieve this objective, and I mentioned some of this last week, I'm going to use cross marks. I've been calling them white lines at regular intervals to allow for in-motion positional updates. Now that data can also be used to help with localization. Cross marks provide absolute positional data with reference to the environment. That's a huge improvement in localization. It'll be easier for me to explain conceptually what the difference is when I get over into that part of the discussion in a few moments. The wheel encoders for most of the travels will only provide data for 1 inch of travel at any given time interval per se. I need it to be as accurate as I can get it within 1 inch, 25 millimeters. Using different color cross marks allows me to add additional logic, or so I thought, to this line following and absolute positioning hybrid system. If I use different colors of markings, I would get different sensor readings, and from that different sensor reading, I could determine different courses of action. And the two primary things that we're marking will be 1-inch markers. Every 1 inch, there will be a marker. For you in the rest of the world, that's 25 millimeters. And then at the end of every line, I need a reset, so to speak, a reference point to start everything over again in the motion tracking. So to me, that made sense that maybe the end of the line would be black and then all the rest of the markers would be white. And then, if needed, if I need more information along any straight road section about positional data, I can use my Hall effect sensors to detect data about the magnet locations. I can embed little 4 millimeter, 5 millimeter neodymium magnets, rare earth magnets, into the surface, see that with a Hall effect sensor and go, aha, that's trying to tell me something unique about this location. Earlier in this whole project, I thought I would use those for stop signs or some other kind of a feedback system. I think they're more useful in this application. Now, about using train tracks, it really has more to do with this. See how this looks along here? While staring at it for many hours in the last week or so, or 2 weeks, 3 weeks, however long I've been working on this concept, I kept thinking to myself, that kind of looks like a train track. So that's all I'm implying here. But the idea of the train track kind of helped feed other ideas of how I'm morphing my original plan on how to do all the traveling and driving and utilizing line following much more. So with that, we're going to move over to the test track. I'm going to show you a lot of the development with regard to markings and so forth so that we can start to make sense of this. Early on, I started out with this line right here. These are just white tape. By the way, I have been on a shopping spree buying all kinds of tape to help with this experiment. Different colors, different glossinesses, every different thing. Some of this is, this one's an actual made specifically for automotive pinstriping. This one and this one are made specifically for whiteboard line marking. People like to put black lines on their whiteboard to help with organizing the graphics as they draw them. These are, let's see, this one is also really horrible. Got it off of Amazon, and this vendor sells all kinds of this stuff, but it's absolute garbage. Oracal, I think, is the brand name. Oh, worst tape I've ever seen in my life. But that was a glossy automotive pinstripe tape. I would hope nobody puts that on a car. You'll destroy the car. These are fine line masking tapes. These are used to help mask around corners in automotive graphics or any other type of painting. You can make it go around tight radiuses so that you can mark them off and prevent overspray from getting into the areas you don't work. I've got this in white, which is what you see here, yellow, green, and there's other colors too, but this is what I had. Black masking tape, blue painter's tape. A lot of variety here, so I tested out a lot of different stuff, and I'll show you a section of the test track in a minute with that. But it helped educate me substantially on what it is we're doing here. Now, as you can imagine, we talked about the line following line. That's this area here. It's a white stripe between two medium or light gray stripes. our photoelectric sensor, located here, senses that line, and it can easily detect if it's this way or this way of the line, and then we read that and tell it to go straight again. And that is working very good, very robustly. But we can't keep track of position. If I start here, by the time I get to here, I can be a ½ inch to an inch off. That would be 13 to 25 millimeters. And that has to do with the fact that anytime this steers, as it's going along here, it is traveling a greater distance than if it were going in a perfect laser straight line. I discovered that through a lot of trial and error, and I was very surprised by how much the distance traveled changes with steering corrections. Moving from there, the idea was, okay, as this passes over, I could have these marks as I've got, and I can see that. And it'd be a different sensor reading between this area and, of course, over the white line. That would allow me to go, okay, at this point, and using typical input logic, when it transitions from, we'll call it line following to white tape, the signal would go high. And then when it gets to the far side of it, the signal would go low. And so I would then figure, okay, if these are evenly spaced, for every time I see the signal go low, I've traveled 1 inch since the last time that occurred. And the really cool part is, if I know where the start of the line is, as in over here I've got a black piece of tape, if I know where that is, and we call that 0, I know exactly where each one of these stripes is, to within probably about 0.1 millimeters if I put the tape down accurate, so about 0.004 of an inch. I know exactly where each one of those is, not relative to the Zoomy, but in an absolute condition relative to the layout. It's nice that the Zoomy thinks it knows where it is, but these markers tell it exactly where it is in relationship to the layout. And that I'm referencing as absolute markings, because in the old system, I would say travel 7 marks. So it'd travel 7 marks. On the new system, starting from back here or anywhere, I tell it to go to position number 20. Well, we'll say 25, this one. Well, at this point, it's only about 18 marks away, but I'm telling it to go to position 25. So as long as this gets a starting reference, which it did back here, there might have been a move here, and then a stop, and now a new move. Well, if I keep track of where it was, I go down to position 25, it will get there. It will not go 25 additional steps from back here. That helps dramatically with keeping track of the Zoomy's position relative to its location on the layout. And the same is true when I get over into the ZOOMTOWN layout. So this system accommodated that, and has tested very reliably so far. Now that's pretty easy, if we consider the Zoomy coming around the corner like this, and okay, we hit the line, and everything is relative, that's my 0 point. But that only works when I start off on a line. What if I'm in a driveway? We just turned on the whole system. The Zoomy has to back out of the driveway, and yes, I know I'm going to be driving on the wrong side of the road, but we'll say it goes like this, gets to about here, pivots on wheel. Now at some position here, the sensors will be picking up our line following line and probably a white marker line. May or may not. It might end up backing out of the driveway here, or here, or here. Well, that's a problem because I don't have a reference starting point anymore, and I truthfully couldn't rely on telling it, okay, you are at this position, left to right. We'll call it 14 inches, because that's exactly what this mark is. Well, if this backs out and it wanders a little bit, and it gets to the far side of 14, the marker, this one, and then I start from here, and then it thinks this is 14, I'm off by an inch. So how do I get a mid-movement reference surface? And I was thinking about different colored tape again. For example, I would use green to indicate this is going to be 14 inches. So when you come out and you see green, that'll be your 14-inch point. That, in theory, was a really cool idea. Practice, it won't work. Primarily because our sensor can't detect enough color distance. Remember, this is only detecting a shade of gray, so to speak. And the difference between the green tape, the yellow tape, the white tape, and the very white glossy tape is almost nothing. So that really wasn't real helpful. But I can put magnets in the roadway. So now, let's say the driveway's here, I back out. Now, I can provide instructions to this saying, the next time you encounter a white tape and a magnet on the right Hall effect sensor, it would be here. When you encounter that, you will be exactly at position 20 inches. Now, again, I'll say I need to go to 25 inches from that point. It's not going to go 25 inches. It's going to go to the position of 25 inches. So that's 1, 2, 3, 4, 5. So if I told it to go to 25, it will move to that point, and it should be 25. It's a little bit hard to wrap your brain around. Anybody that's been in the CNC machine tool business or drawing graphs and so forth, X, Y, absolute and incremental coordinates, this is very natural. And so I'm kind of stealing this idea literally from the CNC industry. Now, the part that I got more from CNC had to do with utilizing two sets of encoders. We have our encoders on the wheel. We know that their amount of error over a great distance can be substantial, but the amount of error moving 1 inch is very minimal. So what I'm doing, I use these white lines as we'll call it an absolute marker. Every white line is 1 inch away. I can get the system to understand where the zoom is when it hits a magnet or the start of the line. That's easy. I will have to count some of the lines in between, but I'm less concerned about counting and more concerned about detecting the exact transition from either low to high or high to low as it transitions over the tape. That is critical. With that, I can easily figure out where I am. So I'm using two encoding systems here. I'm using our photosensors to observe these lines as an absolute reference to where I am on the layout and in 1 inch increments. And this would be considered a linear encoder, technically a system because it's multiple components, but a linear encoder goes in a straight line. Rotary encoders go in a circular motion. So this encoder, only thing I'm using it for now essentially is if I'm on an area of the road where there won't be markings going around a curve, but once I'm into the normal straight lines of all roads, I will be using these sensors with that marker to find out where I am at 1 inch intervals, and then for the distance between, I will use the wheel encoders, both of them, average to figure out where I am as I transition in there for our very fine resolution moves. Very different type of system. It's utilizing essentially 2 photoelectric sensors, 2 Hall effect sensors, and some math. and 2 rotary encoders to really pull all these elements together to give us a greater level of precision and localization. Now, as I mentioned, this comes out of the CNC industry, this methodology of using rotary encoders, which are always found on the servo motor, on the motor's shaft, not at the output end of a gearbox, and then external to that like we're currently using. We lose a lot of precision in there. So a CNC machine on real high precision, high-end machines, you've got the rotary encoder on the servo motor. Then attached to the sliding components, the saddle or whatever you want to refer to it as, but we'll say the x-axis table will have a bracket on it that'll hold the read head of a linear encoder that nowadays they're sub-micron in precision, so extremely accurate. And that will actually track the linear movement and position of that axis as it's moving in either direction. And that's what we're replicating here, only in a very primitive way. But so far, the test data is showing a lot of promise in solving a lot of the problems that I've encountered so far. So with that, we're going to take a look at some of the test data now. As you folks know, I love to graph out data coming from a variety of sensors that I'm working with. It tells you so much more about what's happening than just looking at the raw numbers, especially when you've got, in this case, 2 columns of numbers that the length of it is 3, 4, 5, 6, 7, 944 lines of data. That's a lot of stuff to try to keep in your head and develop a mental image of what that data is showing you. So let's get into this. Excuse me. This particular graph is normal line following with no cross line markers. And this is on the ZOOMTOWN road surface over there. Now that one, the dark gray background, the normal road surface is a dark gray. Over at Test Track Z, you'll notice it's black, kind of a glossy black, which has always been a problem while I'm filming on it. So I'm going to have definitely different levels of readings between the two, and I've got to take that into account while I'm getting all of this prepared for when we move over to the ZOOMTOWN track. But this is the data. Now, the number that I picked from practical testing to switch from reading our line following data and reading where a white line is on the road, the cross line. The cross line I'm representing here at the peak with this yellow line here, and that's at a value of 62,250, which you can see in this column of numbers. The sensor that we're working with will give me a reading from roughly, we'll say 0 up to 65,000, we'll say, just as a simple number to work with. But when I get up to that extreme area there, you're going to see it gets a little bit confusing and dicey. But nonetheless, that was a number that I was reaching. Anytime I moved the Zoomy right over the white line, it would be above that 62,000 mark. So figured as it'd be a good starting point. But here we're just doing a line following maneuver, driving in a straight line. One wheel is doing all the steering, and the other wheel is just kind of going along for the ride. So you can kind of see the difference in adjustment between the two wheels. I'm guessing, well, blue would be the left wheel, red line is the right wheel, yellow line is our limit. But you see it pretty straight, and you see these values are extremely close to the yellow line. Now that again was ZOOMTOWN. Now we'll do a similar run over on Test Track Z. Here you can see both wheels are steering, and you see a lot of adjustment. But it's basically in the range of, we'll say, 50,000 to maybe about 56,000. That's the normal line following range, as long as I don't go over and poke at it and knock it out of alignment, and then it spikes real high. So working with this and our yellow line at 62,250, there's a nice separation between these two in this simple example. So this was really important information. I know I got to really watch for this. I'm going to have higher background readings with ZOOMTOWN because of dark gray background, lower or a greater difference here on the test track because of its black background. That'll pull all these numbers down further and further because they're further and further away from the white line. Now I also did another test, and I'm going to spin the test track around. We'll bounce over to that camera for a minute and be right back. Let's see. Okay. See over here, let me get this out of the way. That's one of my other mics. In the way this was working, I was starting at this end, going across two black lines, these two black lines, these two black lines, these two black lines, and these two black lines. 4 different types of tape and 2 marks with each. I wanted to see if there was any real difference in those readings. Then I figured this dark blue tape would be a nice step, but enough change where I might be able to use that as like a dark gray reading. The 2 green, figuring that would maybe be darker, interpreted darker than the gray on the line following. Then we're into a flat white, a gloss white, and then this line is my yellow tape. So I run it across that and then look at all the readings. Over here, back in the graph, I did this 2 different times, so I won't go through all the details on both of them, but in this one I just did gloss black, the same tape I scuffed up with a Scotch-Brite or fine sandpaper, so it was less glossy, flat black tape, which was the black masking tape, blue painter's tape, green tape, flat white tape, and gloss white tape. Now the interesting thing is the blue and red lines here that are going up and down are the sensor readings. Notice this. They are extremely similar, no matter which color, from the blue all the way to the gloss white. Now I was expecting to see a lot more deviation on that. It just isn't there. The sensor is not seeing enough deviation. Once it interprets that color, what it's really looking at is just a shade of gray in infrared version of that. So there just isn't enough deviation. It just can't detect any more than that. It's not looking at color. So kind of one of those, well, duh, it's not reading color. It's looking at shades of gray on reflected infrared light. So here you can see right away the answer to one of my desires. No, I can't use different color tape to use for different logic situations. There's not enough discernible difference. Sort of. If I look at the white, that's way up here. If I look at black, it's way down here. So I could use white and black, but you'll see that's a problem as well. But what we're looking at with the horizontal lines, this yellow line here is the lower limit in this graph, the lower limit of normal range. So say 51,000, give or take a little bit. This is the upper limit of the normal range at about 58,000. So that's just line following. That's what line following looks like. And this is every piece of tape. The maximum reading would be in that 62,000 range, and you'll notice every one of those hit with pretty darn good accuracy. Now with our black tapes, the sensor doesn't get a higher number, it gets a lower number when it sees black. And that's these dropping down. Now you'll notice gloss black had some weird spiky stuff going on in there, right? Whereas the scuffed black, we have one drop and then one rise. Now these are intermittent. It's trying to go back off and then on and off and on. It isn't doing it in this area, but in this area it is. The flat black behaved a lot like the gloss black. What that tells me right there, the gloss and the reflections caused by it are going to give me a lot of problems with inconsistent reading. Gloss black is a bad thing for what we're doing. Well, once I saw this data, I thought, well, let's put a couple more colors on there to see if it behaves any different. And another brand of tape to see if that would help in the black category, and then our yellow tape. Let's look at the yellow one first. Notice that yellow, gloss white, flat white, green tape, and blue tape all peak at the same range. So what we're really seeing there is that's at the far end of what the sensor can differentiate. It's kind of like the dead end. Once you get to there, it ain't going to show much difference or any higher of a value. So that's why we kind of see that flat lined out. Now the bottom ends, again, the lower levels, this stuff's all in the range of reading the tape or reading the line. And that's what you're seeing in this group. The black tapes, this one, flat black, scuffed, and gloss black, behave very much the same on the second go around. You'll still see the static on the gloss. On the scuffed, it's still beautiful, and the flat is beautiful. And that'll make more sense in a minute. And then this brand of tape from, I think the manufacturer was GGR, that's why I put a note there. It still gives me a good range, and it's pre-scuffed, we'll call it. And I thought, well, then I wouldn't have to scuff up all this tape as I apply all of it. There's going to be probably 1,000, maybe more pieces of tape I'm going to have to put in ZOOMTOWN. I am a little bit on the lazy side sometimes. So what is this data really telling us? Well, if we go to the detailed view, it will make more sense. This is that matte black GGR marking tape, which was this one over here. This is the gloss white marking tape, which was the one right here. And the reason why I kind of picked that is it seemed to have the greatest range of readings. So I took those two sets of data to explain what I'm looking for. We see kind of this waveform, right? You see it go up and down, and we would consider that amplitude, the amount of range that we're getting in the reading as it passes over the tape. So my amplitude, my range of change, is much greater on the black tape than it is over here on the white tape. Notice a very, very shallow or small amplitude. This next one was the discovery I was actually looking for, and I'll explain the problem in a minute. This is the distance on the transition. What I mean by that, the yellow line, as it was in one of the first samples I showed you, was that 62,250 line. The way I was going to do that, if the reading, both sensors read over 62,250, I'm on top of white tape. Anything below that, I'm just doing normal line following, which is exactly what we see there, right? Now with black tape, I don't go higher, I go lower, so I would have a number, say, down here at about 4,000, where I'm looking for any number or any value below 40,000, I would consider I'm sitting on top of black tape. Well, notice the contact area over this whole distance. Now down here are the counters, so that we'll say that was about 80, 82, 83 readings. Or I'm sorry, 12 to 13 readings as it's on top of the tape. And that's every 6 milliseconds it's taking a reading. So let's keep that part straight. Now, in this whole range here, over that distance, you can see that both the red and the blue lines are going above and below our yellow line. So instead of getting one on signal, and it stays on, and then one off signal, I'm getting on, off, on, off, on, off. It's jumping back and forth in there because it's right on the edge of the line with a value. We're at 62,240 here, but 6 milliseconds later, I'm over 62,250. 6 milliseconds later, I could drop below. It's that close. There's not enough differential between the readings of normal and being on white tape. That caused me a problem I'll talk about in a minute. So with that, I'm was really pleased to see how the graph showed me the data so I could understand the behavior. Now with the black tape, the interesting thing is, notice how here we're dealing with a gradual drop. It's a very gradual slope on and off. So it's like turning a light switch on really slow. If you're familiar with old mechanical switches, if you turn them on slow, you'll even hear them arcing because it's not on, it's not off, but it's really close. In the digital world like we're seeing, we can get these on-off states that we don't want, and they're very unexpected. Well, in this area, notice how very vertical, the line is much more vertical than horizontal in the transition between on and off. And my distance on that transition is a very short distance, maybe 6, maybe 12 milliseconds. The more steep that angle is on either side of going onto the tape or off the tape, I'm limiting my probability of getting multiple on-off states during that transition. That was a huge discovery for me. And we're going to go back to here. Now notice also here, we've got on the scuff gloss black and the flat black, a much cleaner line going much steeper up and down. So if I said my threshold was at 30,000, which would be right here, there would be a distinct singular on state and a singular off state in a very short period of time. And that's what we wanted. Now, what was the problem I was having? Let's go back to Test Track Z. I had got this to seemingly 100% reliability. And what would happen, occasionally it would miss by 1 or 2 inches, 25 or 50 millimeters. And I could not figure out how it could not count this, because I could easily see, just glancing at the data, it's seeing the line, so how can it miscount? And they're pretty far apart. What was happening? Well, as I mentioned, up here in this area on any of these colors, which is what I'm testing there, I'm testing flat white, this one, so this would be the data set. It is going, let's say I'm going from left to right. We get on, that is the beginning of the tape. Right here I can see below, so that's the end of the tape. Well then right away it goes back on again, and then off. And it was happening only occasionally, simply because of the values being so close together. There wasn't enough differential to have a safe zone or a buffer zone between on and off for the reading sitting over the tape. The net result was this, and this is where we'll kind of conclude this story. This data right here really tells me I should focus on this, either flat black mask tape or scuffed gloss black tape. I will now decide based on the adhesion characteristics of those two tapes, and of course if I can find the narrow black tape. I don't want to sit and hand cut the width along with the length of each tape marker. Again, I'm a little on the lazy side. So that is what I am going to do. I will work with black lines, black marker lines, and because I can't really rely on any of these colors to give me another color choice, I will then work on magnets. Back to Test Track Z. For the purposes of, as the example earlier, I back out of the driveway, I'm somewhere in this area, and I know the next time I see a white line with a magnet marker on the right sensor, I have a predetermined position to call this. And in this case, it would be 20 inches. And then from there, if I'm telling it to go to 25, it knows to go to here. Left Hall effect sensor, black line, is the start of a line. Start of the new line or end of the old line, however I want to reason that out in logic. Then black tape and a magnet on the right Hall effect sensor will be a mid-traveler, a mid-line set point that I can pass through from the scheduler in the navigation directions to say, you back out of this driveway, you will encounter a black line with a magnet on the right side, and that will be position 21 or whatever it is. And then from there, we can find ourselves very easily and accurately backing out of a driveway. So that's where we're at today. This is the video I'm filming today. It's Thursday, 6/27. So hopefully I'll get it edited and ready for you guys tomorrow morning. And then over the weekend, I'm going to really be messing around with this a lot. I'm not quite ready to move this over to ZOOMTOWN. I still kind of want to work with Test Track Z, even though it's going to corrupt my data a bit. But I kind of need to, I don't want to do a lot of work over there because it gets a lot more scaled up. As you can imagine, there's a lot more roadway there than there is on Test Track Z. So I want to be very careful of how I do this. My time is very precious to me. So that's it for today. My mood and spirits are back positive, and we're moving forward in a great direction. So again, I want to thank everybody for your kind words, your comments, your suggestions, encouragement. It all helps. And for me, the whole thing, no matter what, even the bad days with Lucinda Williams bumming me out with her songs, it's all good and fun, and I really enjoy doing this and sharing it with you guys. Hopefully I can see you next week if I can get another video ready for you. Thanks for watching.